So in today's lecture, we're going to talk about the concepts of impulse and momentum. So what they are and how they're used. So again, these are words which you have undoubtedly heard in everyday language. So for example, you may be familiar with an impulse buy, or you might lose momentum when solving physics problems, for example. But just like we saw with work and energy, these concepts have technical definitions in physics, as we will see very soon. So the first main goal for today's lecture is to get you all familiar with the impulse momentum theorem. But luckily, we will cover it quite early in today's lecture. Now, the second main goal of today's lectures is to introduce how physics handles collisions. So collisions will be our second main topic for today. So today's lecture is going to be a relatively short one. So if you have any questions at all, please shout it out or type it into the chat. Now to start with, I will begin by telling you all that I lied to you in last week's lectures. I told you all that Newton wrote down his second law as the sum of the forces acting on an object is equal to the mass of that object times that object's net acceleration. But Newton, at the time of writing Principia, which is where all of this comes from, didn't use the concepts of acceleration, but instead used some quantity called the momentum of an object. He believed that the quintessential motion of an object was captured by this physical quantity, which we will define here. So to start with, we're going to start by defining definition. We're going to define linear momentum. So the linear momentum of an object is denoted by this vector p, and it is a vector, so the momentum's a vector. And this linear momentum is going to be equal to the mass of the object times the velocity of the object, right? Just box this off. So this here is what we call the linear momentum. Just highlight this. So the momentum, the linear momentum, is going to have units of, and so note how we actually define the momentum. It's the mass times the velocity. So the mass has units of kilograms, and the velocity has units of meters per second. So units of momentum are kilograms times meters per second. But this is the same as a Newton times a second, if you will. All right. So you could use either of these units when talking about momentum. They're both equivalent to one another. So if you want to increase the momentum of an object, you can increase its mass, or you can increase its velocity. So let's look at a quick problem talking about linear momentum. So example 1. So example 1. So example 1 says, find the momentum of a 10 kilogram box, which is moving at a speed of 20 meters per second. Which is moving at a speed of 20 meters per second. So it's kind of short. So in this case, this is an example of a 1D problem. So we're going to indicate our vector by whether it's positive or negative, right? It's either moving to the right if it's positive, or it's moving to the left if it's negative. So the mass of our object is 10 kilograms. And the velocity of our object, our velocity v, is positive 20 meters per second. So it's going to the right. So in this case, our momentum is just this mass times this velocity. So it's going to be our mass of 10 kilograms times our velocity of 20 meters per second to the right. And this gives us an answer of 200 kilograms times meters per second. All right, where in this case, the fact that this is positive indicates that the momentum is pointing to the right. All right, so fairly short problem. Before I tell you guys how I lied to you in the previous weeks, I first have to explain what the impulse of a force on an object actually means. So let's define that now. And then I can tell you how I lied. So we're going to define next. Define the impulse of a force. Impulse of a force. Impulses are always associated with a force, and we define the impulse as a vector j. It's going to be equal to the average force acting on an object multiplied by the time that that force is acting on that object. So this j here, this j is what we call the impulse caused by this force. This here is the average force. That's what that little bar over it means. So it's the average force. And then delta t is just the time that that force is acting. So maybe I'll bring that down here. Time that the force is acting on our object. On our object. So let me really quickly just box this off. There we go. We're going to highlight that. And so this has units of, all right, so looking at our definition, we have a force, which is a unit of newtons, and we have time, which is going to have units of seconds. So the units for this are going to be a newton times a second, right? Which, if you remember, is pretty much the same thing we had for the linear momentum. So right off the bat, this kind of tells you that impulse and momentum are somewhat related. But first, let's work a quick example with impulse. So this is going to be example 2. So example 2. So example 2 says an average force of 10 newtons is exerted for 0.2 seconds. It's exerted for 0.2 seconds on a box. And the problem wants us to find the impulse. Find the impulse, of this force on the box. So the impulse is a vector. So we need to keep that in mind. So to find the impulse for this, right, it's going to be our impulse j is going to be equal to the average force acting on our object times the time that that force is acting on that object for. So in this case, our force is 10 newtons. Right, our average force is 10 newtons. And the fact that it's positive 10 newtons indicates that, the force is pointing to the right in the horizontal direction. And it's exerted for 0.2 seconds. So the time delta t is 0.2 seconds. And so we get an impulse of 2 Newton seconds. I know it's kind of weird, but our impulse is 2 newtons times seconds. Right. So that's the end of example 2. So now I can tell you how I lied. So Newton originally wrote his second law, saying that the net force acting on an object was equal to that object's change in linear momentum divided by the elapsed time. So I'll put maybe in parentheses Newton's real second law. And so Newton's real second law, quote unquote, right, the way he wrote it, says that the force acting on an object is equal to the change in momentum of that object divided by the elapsed time. Right? Where delta P is equal to our final momentum minus our initial momentum. Right? So this initial momentum is, the momentum of our object, before the force is being applied. This final momentum PF is the momentum of our object after the force has been applied. And delta T is the elapsed time. So notice what happens if I take this and I multiply both sides by delta T. So when I do that, I get that on the left-hand side, the average force times the elapsed time is equal to delta P. This leads us to the impulse momentum theorem. Right, so the impulse momentum theorem says pretty much just what I've written down here. So this thing on the left-hand side, you'll recognize is how we define our impulse. And this thing on the right is our change in our linear momentum. So the impulse momentum theorem literally says that our impulse, J, which is equal to the average force multiplied by the elapsed time that force is acting on our object, is equal to the change in linear momentum of our object. So final momentum minus our initial momentum. So we know how to define momentum, right? Because we looked at that the first thing we saw in this lecture was that. So the final momentum is just the mass of our object times our object's final velocity minus our initial momentum, which is our mass, times our object's initial velocity, like that. And this whole thing is called the impulse momentum theorem. There we go. So let's look at an example using the impulse momentum theorem. So this will be example 3. Example 3. So example 3 says that a baseball with mass 0.14 kilograms has an initial velocity, which is V naught is equal to minus 38 meters per second. It's 38 meters per second as it approaches a bat. As it approaches a bat. Right, the problem goes on to say that we have chosen the direction of approach as the negative direction, right? So this ball is initially coming in from the right side, and it's going towards the bat, which is somewhere over here. So the bat applies an average force. The bat applies an average force. That is much larger than the weight of the ball. That is much larger than the weight of the ball. And I'll explain what that means at the end. And the ball departs from the bat. And the ball departs from the bat with a final velocity, of 58 meters per second. Now, let me just write VF, which is positive 58 meters per second. So the problem wants us to determine the impulse applied to the ball by the bat. So part A, determine the impulse applied to the ball by the bat. Applied to the ball by the bat. And so this is part A. Part B is asking, assuming that the time of contact, so assuming that the time of contact is delta t is equal to 1.6 times 10 to the negative 3 seconds. Part B is asking us to find the average force exerted on the ball by the bat. So find the average force exerted on the ball by the bat. All right, so that's all example 3. So for the part here that says that the bat applies of average force that's much larger than the weight of the ball, that's just physics speak. That says the magnitude of the force acting on the ball is so much greater than the weight of the force of gravity acting on the ball that we can basically ignore it. So that's all that means. So let's assume that right here on the left-hand side, we have our bat. So this area over here is our bat. So the ball is initially coming in. This is our ball. It's initially coming in with some initial velocity v, and that velocity has a magnitude of 38 meters per second. And then after it hits the bat, right, it gets hit by the bat, and then the ball ends up going in the other direction with a final velocity of 58 meters per second. It will be final, right? And so the problem is asking us to calculate first the impulse applied to the ball by the bat. And then part B is asking, well, if we know the time that the ball is touching the bat, what's the average force exerted on the ball by the bat? So to begin with, if we want to calculate the impulse applied to the ball by the bat, right, we know that the impulse is equal to, right, if we go back to our impulse momentum theorem, we know that the impulse of a force is equal to the change in momentum of that object. So in this case, we can calculate the change in momentum. That's equal to delta p. Delta p is just our final momentum minus our initial momentum. Skip a step. Initial momentum. Right. Now we actually put in our initial and final values for momentum. Right. So the mass of this ball is 0.14 kilograms. The initial velocity is minus 38 meters per second. Or the minus sign indicates that it's going to the left. And our final velocity is just 58 meters per second to the right. So we want to calculate the impulse, right? We just got to plug in our values for the mass and our velocities here. So our impulse is equal to the mass of the ball. And in fact, I can actually factor this mass out of both since it's applying to the same object. It's the same mass. This is equal to the mass times our final velocity minus our initial velocity. So our mass is 0.14 kilograms. And then our change in velocity is our final velocity, 58 meters per second, minus our initial velocity, which is minus 38 meters per second, right? And so this minus sign gets canceled by this minus sign. So we ended up with a plus sign. So this becomes our impulse is going to be equal to 13.4 kilograms times meters per second. So this is the impulse of the bat on the ball. So this is part A. So part A. Now part B is saying that we know the time that the ball is touching the bat. So this time, I guess for part B, let's say that this time delta t is what, 1.6 times 10 to the negative 3 seconds. And we want to find the average force exerted on the bat. All right, so what is that average force? But by the definition of impulse, we know that the impulse is equal to the average force on an object times the time that that force is acting on that object. So all we've got to do, right, we found what the impulse was in the previous part, and the problem gives us delta t. So we just have to divide both sides by delta t to find the average force being applied to the bat. So let's do that now. So we know that the force, the average force, is equal to the impulse divided by the time that our force is acting on our object. Right, so we saw that our impulse was 13.4 kilograms times meters per second. And delta t was a very short time. It's 1.6 times 10 to the negative 3 seconds. So 1.6 milliseconds. And this gives us an average force being applied to our ball of 8,400 newtons. 8,400 newtons. So this is the answer to part B. So after all of this, you might go and say, well, that's great, but now we have to study more stuff for the exam on Friday, right? Why did we even learn about this stuff anyway? What's so good about impulses and momentums? Didn't we already have everything we needed back when we were talking about velocities and accelerations and all that? Why go and make this more complicated? So the reason why we bother with momentums and impulses at all is similar to why we worked with work and energy in the last lecture. In certain situations, the total momentum of our system is conserved. So we will now talk about the principle of conservation of linear momentum. So let me just write that down. So now we're going to be talking about the principle of conservation of linear momentum. There we go. So, as a side note, this applies for an isolated system. So for an isolated system, right? And that means for a system with no external forces acting on our object. The conservation of linear momentum says that if we add up the momentum, for all of our particles initially for our system, right? And then we let our system evolve in time, right? We wait a little bit and then we look at the momentum afterwards, right? The momentum of all of our particles in our system afterwards are going to be the same. So what this is saying is the momentum of our system initially, right, if momentum is conserved, is equal to the total momentum of our system after we let it evolve. So in general, we really like to see conservation laws in physics. The more conservation laws we have, the more easily or precisely we can solve for our equations of motion, or our charge density, or the heat transfer between two bodies in thermal equilibrium, or the dynamics of a black hole's motion, right? Conservation laws typically tell us that something is conserved in our physical system from one moment to the next. And by knowing what those conserved quantities are, we can solve for whatever we wish to solve for. So it works the other way also. If we know that, for example, the total linear momentum of our system should be conserved, but when we actually run the experiment, we see that some of it went missing, then we can immediately figure out that there is a previously unknown external force acting on the total linear momentum of our system, right? There's some unaccounted force in our experiment. And this happens all the time in physics. So in fact, most of particle physics was built by looking at energy and linear momentum conservation laws and seeing that after two particles collided, we were missing a bit of energy here or some linear momentum there. And that led us to speculate that there was another sneaky particle stealing away some of the system's energy and momentum. So this sort of thing led us to find particles such as the neutrino, which is an incredibly light particle that interacts so weakly with its surroundings that it could pass through a wall of solid lead a light year thick without being affected in the slightest. So in fact, there's actually trillions upon trillions of neutrinos passing harmlessly through you all the time, every second of the day. Because the neutrinos interact so weakly with everything, we wouldn't have been able to figure them out by running an experiment, right? We wouldn't have been able to detect them since they don't really interact with anything that we can really detect super easily. There are experiments that are set up in order to find and detect neutrinos, but unless we knew specifically what we were looking for, we might not have made those experiments at all. So the way that we found this is by looking at what an experiment should be and seeing that there was something missing. And because that thing was missing, we were like, okay, well, there's some particle we don't know about. So all of this is because of conservation laws. So when we talk about things like the conservation of energy of a system or the conservation of a system's linear momentum, these are important concepts in physics. And the more of these conservation laws you have, the better. So this leads us to our next section, which is going to be called collisions in one dimension. Actually, this is important, so let me box it off. Everything important in physics gets a box, apparently. Even the problems themselves. So for our next topic, we're going to be talking about collisions in one dimension. All right, so two objects bump into each other where each of these objects is moving along, a straight line. So in general, there are two types of collisions that we care about. There's elastic collisions and inelastic collisions. So there are two, let me call these ideal types of collisions. And I'll talk about this more after. So the first type is called elastic collisions. Elastic collisions. The second type is called inelastic. Inelastic collisions. All right, so why did I say, there are two ideal types? because no collision in nature is perfectly elastic or inelastic. Well, on the macroscopic scale, excuse me, right? When we're dealing with things like particles, right, like neutrons and protons and electrons and all that stuff, then there can be elastic collisions. But for something as large as and as complicated as a car, we'll find that if you were to collide with this car, in general, whatever you collided with, that collision would not technically be either elastic or inelastic. It would be some sort of weird mix of both. But it's good to still have these two different types of collisions in mind whenever you're looking at a problem, right? This is physics 1. We can make all these ideal situations come to life when we're actually solving these kinds of problems. So to begin with, let's talk about elastic collisions. So part 1. So elastic collisions. So for elastic collisions, there's two key things that define it. The first thing is that momentum is conserved. And when I say the momentum here, I mean the total momentum. You can't just look at a single particle and expect its momentum to be the same. But if you look at everything that's being collided and you look at all the momentum added together, then the momentum of our system before is going to be equal to the momentum of our system afterwards. So we have the sum of our momentum initially, like before the collision, is going to equal the sum of the momentums of our system after the collision. There we go. And so the second defining thing for an elastic collision is that kinetic energy is conserved. Kinetic energy, which hopefully you guys remember from last class. So kinetic energy is conserved. That is the total kinetic energy of our system before the collision is equal to the total kinetic energy after the collision. So let's look at an example. So this is going to be example, what's the last one? 3. All right, this is going to be example 4. So example 4 is going to be talking about an elastic collision. So this says that a ball of mass 5 kilograms, a ball of mass 5 kilograms, hits another ball, with mass 1 kilogram at rest. 1 kilogram at rest. So the second ball isn't moving. So if the velocity of the first ball, is 10 meters per second, then the problem wants us to find the final velocity of both balls. Find the final velocities of both balls. All right. So let me draw a before and after picture. So this is going to be before collision. All right, so in this case, we have one ball trying to hit another ball. So this ball here is moving to the right. So this initial velocity call this initial velocity for ball 1. So I'm going to call that I'm going to say that the ball that's initially moving in this problem, I'm going to call that ball 1. So the initial velocity of this first ball, 10 meters per second. We know that this thing weighs 5 kilograms. And the second ball over here weighs 1 kilogram, and it's at rest. So the initial velocity of the second ball is going to be 0, because it's initially at rest. And then we're going to draw a picture of after the collision. So after these two balls collide, so after they collide, you know, this first ball is going to have some final velocity. It still weighs 5 kilograms. You know, maybe it's moving to the right, maybe it's moving to the left. I'm not sure, but I'm going to draw it as if it's moving to the right. So we don't know the final velocity of this. And then afterwards, you know, intuitively, we can think that if this first ball was initially at rest, and then it gets hit by another ball from the left, we would expect that afterwards it's going to be traveling to the right. So we're going to need to, I think I'm actually confusing the notation here a bit, so let me actually keep it consistent with our first part. There we go. So we don't know what the final velocities are, but we know that mass of this first ball, or the second ball, is 1 kilogram. All right, so let's begin by trying to solve this problem. So let's look at the initial momentum for our system. So initially, right before the collision, so the initial momentum of our system is just the initial momentum, which is just the mass of the first ball, times the initial velocity of the first ball, plus the mass of the second ball, times the initial velocity of the second ball. Right? But the initial velocity of the second ball was 0. So because of that, this second term is 0. So all of the momentum in our system initially was because of this first ball. So it's just m1 v1. All right, so let's calculate that now. So our initial momentum is the mass of the first ball, which is 5 kilograms, times its initial velocity, which is 10 meters per second. And this is going to give us an initial momentum of 50 kilograms times meters per second. So this is the initial momentum of our system. So for the final momentum, we're going to look at the momentum of our system after the collision. For final momentum, we have our final momentum is going to be equal to the mass of the first ball times the final velocity of our first ball, plus the mass of the second ball times the final velocity of the second ball, just like that. But this is going to be a little bit difficult because, right, we only know the masses, right? We only know m1 and m2. We don't know what the final velocities are for each of these. So in this case, the final momentum of our system is going to be the mass of the first ball, which is 5 kilograms, times the final velocity for our first ball, whatever that is, plus the mass of the second ball times the final velocity of the second ball, again, whatever that is. And because of the conservation of momentum, so we know that the initial momentum of our system is going to be equal to the final momentum of our system. So we know that this is going to be equal to this. Right? So on the left-hand side, we have 50 kilograms times meters per second. Right? This is just literally the conservation of linear momentum. So on the left side, we have our initial momentum of 50 kilograms meters per second. And on the right, we have 5 kilograms times our final velocity for the first ball plus 1 kilogram times the final velocity for our second ball. I know there's a lot of subscripts in this. I'm not overly fond of it, but it's, what we have to deal with if we're trying to do these kinds of problems. So at this point, we can't really do anything more with this. So let's just box this off. All right, let's just box this off, and I'm going to call this equation 1. So in order to solve this, we also need to make use of the second fact for an elastic collision, right? And that is that the kinetic energy of our system is conserved. Right, so conservation of kinetic energy says conservation of kinetic energy right, because this is an elastic collision, right? In general, kinetic energy is not conserved, but because we're dealing with an elastic collision, it will be in this case. So this says that the initial kinetic energy of our system is equal to the final kinetic energy, right? So the kinetic energy before a collision should be equal to the kinetic energy of our system after the collision. So our initial kinetic energy, right, is just the kinetic energy for both. So it's going to be 1/2 times the mass of our first ball times the initial velocity of our first ball squared plus 1/2 times the mass of the second ball times the initial velocity of the second ball squared. But again, our second ball started from rest. So this term is 0, right? Because that's 0. So our initial kinetic energy is just 1/2 times the mass of our first ball, which is 5 kilograms, times its initial velocity magnitude squared. So it's 10 meters per second squared. So in this case, the initial kinetic energy of our system, like before the collision, is 250 joules. Right? So let's look at the kinetic energy afterwards. So the kinetic energy of our system afterwards is a little bit of a nightmare, right? It's 1/2 m1 v1 final squared plus 1/2 m2 times the final velocity of our second ball. But we don't really know what these are, right? So just plugging stuff in, plugging the masses in, we have 1/2 times the mass of m1, but m1 is just 5, so this is just 2.5 kilograms. Right, multiplied by the final velocity of our first ball, squared, whatever that is, plus 1/2 times the mass of our second ball, right? The mass of our second ball is just 1 kilogram, so 1/2 times 1 is 1/2. It's going to be 0.5 kilograms times the final velocity of our second ball squared. And so according to the conservation of kinetic energy in this case, right, our initial kinetic energy should be equal to our final kinetic energy. So then we have that 2.5 kilograms, right, times the final velocity of our first ball squared plus 0.5 kilograms times the final velocity of our second ball squared is equal to 250 joules. And at this point, we can't do anything else with this. So I'm going to call this equation 2. So now we have equation 1 up there and equation 2. So let me just put these together. Right. So the two equations that we have, equations 1 and equations 2. On the one hand, for equation 1, we have that 5 kilograms times the final velocity for our first ball plus 1 kilogram times V2 plus final velocity for our second ball. It's equal to 50 kilograms times meters per second. All right, that's our first equation. And then the second equation we have there, so 2.5. I'm just rewriting this really quickly. Actually, you know what I'm going to do? I'm going to multiply through both sides of equation 2. I'm going to multiply through by 2. All right. So this is going to be 5 kilograms. And this is just going to be 1 kilogram. Right. And since I multiplied the left side by 2, I've also got to multiply the right side by 2. So hopefully everyone's on board with that. Okay. Now what we can do is we can solve equation 1 for, let's say, V2. So if I subtract off this term from both sides, and I divide both sides by 1 kilogram, we get that V2, this is from equation 1, right? We get that the final velocity for our second ball is equal to 50 meters per second minus 5 times V1F, or VF1. Right. So this is what we get by solving equation 1. And so what we can do, we can take this, right? We can take this value for V2 and we can plug it in to our second equation here. This is kind of a pain in the butt, but we got to do it. So I'm going to call this star. All right, so we're going to take equation star and put it into equation 2. So when we do that, we get 5 kilograms times the final velocity squared for our first ball. Right, that's plus 1 kilogram times the final velocity of our second ball squared. But the final velocity of our second ball is just this stuff. So that's 50 meters per second minus 5 times the final velocity of our first ball squared. And that's all equal to 500 joules. Right. Now notice that this left-hand side, right, we're only working with the final velocity for our first ball. So if I take this and I expand out the left-hand side, I can eventually find a quadratic equation form for this equation. So this ends up being equal to 30 times the final velocity for our first ball squared minus 500 times final velocity for first ball plus 2000 joules is equal to 0. So we can use the quadratic formula to try and figure this out. So according to the quadratic formula, our final velocity, the first ball, is 500 plus or minus the square root of b squared, which is 500 minus 4 times the value for a times the value for c. Right, all this under the square root. And then we're dividing all this by 2 times our value for a. So it's going to be 2 times a, which is 2 times 30, which is going to be 60. And so this is going to give us 2 answers. Right? So the 2 answers it gives us is either 10 meters per second, or, right, depending on if we use the plus or minus sign here, the plus sign, right, the plus sign is going to give us 10 meters per second, whereas the minus sign is going to give us a final velocity for our first ball of 6.7 meters per second. Now, in the past, when we used the quadratic formula to try and solve a quadratic equation like we have here, right, we would always take the plus sign, just because that was the physical thing to do, right? Because in the past, if we took the negative sign, that would give us a negative time, which in those cases was not physically valid. But here, I want you guys to think a little bit. If you think back, right, the initial velocity for our first ball, in fact, let me scroll up. The initial velocity for our first ball was 10 meters per second. So it can't make any sense that our first, like after this first ball collides with the second ball, it doesn't make any sense for the velocity of the first ball to remain unchanged, right? We expect this thing to be either going faster or slower, but definitely not staying the same. So in this case, the correct answer is using the minus sign, which gives the final velocity of the first ball to be 6.7 meters per second. And so we can plug this in to right here, right, in order to find, the final velocity of the second ball. So for the second ball, right, that's equal to 50 meters per second minus 5 times the final velocity of our first ball, which is 6.7 meters per second. This is going to give us 16.7 meters per second for the first or the second ball. 16.7 meters per second. So then the final velocity of the second ball is just 16.7 meters per second. Whew. All right. So let's talk about the second type of collision. So the second type of collision are called inelastic collisions. And there's 2 defining things for inelastic collisions. So just like in the elastic case, total momentum is conserved between both, right? So, the initial momentum of our system is equal to the final momentum of our system, after the collision. So this is true for both elastic and inelastic. But the main difference between elastic and inelastic collisions is that for an inelastic collision, the kinetic energy is not conserved. Right, so that's the main point here. Not conserved. So in general, kinetic energy initially is not equal to the kinetic energy of our system afterwards. So there's a subset of inelastic collisions called completely inelastic collisions. So a completely inelastic Elastic collision, right, is where the objects stick together. So after collision, our objects stick together. Right, and if our objects stick together, that means their final velocities have to be the same because they're moving together at the same speed. So the final velocity for our first object is equal to the final velocity of our second object. So let's look at an example. Last example of the day. The last example we looked at was 4. So this is going to be our last example, which is going to be example 5. Just as a side note, the elastic collision calculations we did in the previous example are complicated and annoying, but there's ways of shortening them down. And I won't expect you guys to do something that complicated on an exam, right? In that case, I'll just give you a quick formula to help you guys get through that. But for now, let's look at example 5, which says that a ball with mass 10 kilograms, a ball with mass 10 kilograms is moving to the right, with a velocity of 30 meters per second. Velocity of 30 meters per second. So a second 5 kilogram ball, is moving to the left with a velocity of 50 meters per second. So is moving to the left with a velocity of minus 50 meters per second. So the problem says that they collide and stick together. So the problem wants us to figure out what is the final velocity of each ball. What is the final velocity of each ball? Well, since they both stick together after the collision, this is a completely inelastic collision, right? So the only thing that's being conserved in this problem is the momentum. So let's write down what we know. So ball A1 has mass of 10 kilograms, and the initial velocity of this first ball is 30 meters per second. Right. The mass of the second ball is 5 kilograms, and its initial velocity is moving to the left, the velocity of minus 50 meters per second. And so since they both stick together, they're both going to have the same final velocity, which I'm just going to call VF, right? Since they're both sticking together, it doesn't matter what I call it. And so let's try solving this problem. So to begin with, we know that our momentum is still conserved. So only the momentum is conserved here. So our initial momentum is just the mass of the first ball times the first ball's initial velocity plus the mass of the second ball times the second ball's initial velocity. All right, so this is going to be 10 kilograms times its initial velocity of 30 meters per second plus the mass of the second ball, which is 5 kilograms, times its initial velocity, which is minus 50 meters per second. Right, so this is going to be 300 kilograms meters per second minus 250 kilograms meters per second, which gives us an initial velocity for our system, right before the collision, of 50 kilograms times meters per second. Now afterwards, we need to calculate the final momentum of our system, which is just the mass of the first ball times the final velocity of our first ball plus the mass of the second ball times the final velocity of our second ball. But because this is a completely inelastic collision, right, and our final velocities are going to be the same because they stick together, we can actually factor these two out since they're both exactly the same. So our final momentum is equal to first mass plus our second mass, right, because they stuck together, times the final velocity of both of them. So in this case, right, we have 10 kilograms for the mass of our first ball, it's 5 kilograms for the mass of our second ball, times our final velocity for both of them combined. So this is just 15 kilograms times our final velocity for both of those balls. And because this is a conservation of momentum problem, right, so both the initial momentum of our system and the final momentum of our system are equal. On the left-hand side, we have our initial momentum of 50 kilograms times meters per second. And on the right-hand side, we have our final momentum of 15 kilograms times our final velocity for both ball 1 and ball 2. Now, if I divide both sides by 15 kilograms, we get a final velocity for both ball 1 and ball 2 of 3.3 meters per second. And that's our whole problem. See, this one was much easier. And with that, that's all I've got for you guys today. So if you have any questions, please feel free to ask. And I'll see you tomorrow.